X plus Y stars Asa Butterfield as Nathan, an autistic teenager who struggles through social challenges and psychological trauma as he pursues his dream of competing in the International Mathematical Olympiad. The film is also known in the US as A Brilliant Young Mind, somehow an even worse title. Like many films centered on mathematicians, it teases the audience with a few mathematical problems and solutions. But, as we know, most films spout mathematical jargon with no regard for accuracy. This is where X plus Y surprised me. So welcome to Maths, a series where I rank films on a 2-axis scale based on their accuracy and quality. This one will be a bit more mathematical than my previous videos in the series, and that's because in X plus Y we do see some fully presented problems, and the solutions are well worth delving into. I hope you enjoy. X plus Y follows Nathan as he prepares for and competes in the International Mathematical Olympiad. If you're unaware, the IMO is one of the most prestigious mathematical contests for high schoolers and involves a rigorous training and selection process, with each country submitting 6 candidates. The questions are hard, often involving mathematics far beyond high school curricula. What I love about X plus Y is that many problems are stated in full, practically begging the audience to attempt them for themselves. If you've never attempted this style of question before, it can be quite daunting. Even if a problem doesn't involve any advanced mathematics, seeing how to apply your knowledge can be difficult. I know because I recently attended a mock Oxford interview with Tom Rocks Maths, and you can check that out here. Some problems require clever reframings or demand certain problem-solving techniques, and I was surprised to find a rich source of lessons and exercises to hone these skills at Brilliant.org. This video's sponsor. Brilliant has 2 dedicated courses on contest maths, which provide plenty of opportunities to learn and practice these skills. I was shocked at how extensive these courses are, each with over 60 lessons but broken into manageable bite-sized chunks so you never feel overwhelmed. Not only that, but they teach extra pieces of mathematics not always seen at school, but which are seen on many Olympiad-style questions. Things like the Cauchy-Schwarz inequality or Euler's totient theorem. Even if you never plan to enter a contest, these courses are the perfect way to strengthen your mathematical skills. Whether these courses are for you or whether you want to learn some physics or computer science, Brilliant is the best way to learn, meeting you at your level and then tailoring the experience to meet your needs. Try everything Brilliant has to offer today for 1 month at brilliant.org/anotherroof. The first 200 of you to sign up using this link will get 20% off their annual subscription. That's brilliant.org/anotherroof or use code anotherroof at checkout. Thanks to Brilliant for supporting my channel. Back to X plus Y, and let's look at the first problem. It's given in the paper that Nathan sits to be selected for the candidate shortlist.
Are there infinitely many pairs of positive integers, mn, such that both m divides n squared plus 1 and that n divides m squared plus 1?
Before we discuss the problem, I just want to say that this problem just feels so Olympiad. There's a certain type of question that students are tested on, and this is it. Fairly easily stated and often quite difficult to get into. Pause if you want to give this problem a go, it's well worth it. If you're struggling, try playing my solution step by step to get hints. You might start with some experimentation, computing n squared plus 1 for the first few natural numbers. And remember, the kind of pairs that we're looking for will be such that the first divides the second's square plus 1, and the second divides the first's square plus 1. So here we can obviously see that 1, 3 doesn't work, as 3 doesn't divide 2. But the pair 1, 2 does work, as 1 divides 5 and 2 divides 2. We can also see that 2, 5 works, as 2 divides 26 and 5 divides 5. But can we find any more? Well, suppose that 3 had a partner. Then its partner would have to be a number that divides 10. The only such numbers are 1, 2, 5, and 10. We see that 1, 2, and 5 don't work, as 3 doesn't divide any of their squares plus 1. So what about 10? Well, 10 squared plus 1 is 101, and 3 doesn't divide that either, so 3 doesn't have any partners. Similar reasoning shows that 4 can't have a partner, as 17, being prime, is only divisible by 1 and 17, but 17 squared plus 1 is 290, and 4 doesn't divide that. However, one of the divisors of 26 is 13, and 13 squared plus 1 is 170, and 5 does divide that. So 5 divides 13 squared plus 1, and 13 divides 5 squared plus 1, so 5, 13 is a pair. So we've done some experimentation, and now we might notice that all of these pairs seem to be chained together. 1, 2, 2, 5, 5, 13, What comes next? Well, let's see if 13 can be paired with anything. 13 squared plus 1 is 170, and when we look at its factors, I'll spare you all of the details, but we realise that 34 will partner with 13, as 13 squared plus 1 is 1157, which does have 13 as a factor. So 13 partners with 34, and do you see the pattern? Pause now if you want to see if you can spot it, because there is a pattern in these numbers. Well done if you spotted it. These are all Fibonacci numbers. Specifically, they are the terms in the odd position of the Fibonacci sequence. And I'm sure you've all seen the Fibonacci sequence before, but in case you haven't, it's the sequence generated by 1, 1, and then the next term is the sum of the previous two. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. The next term in odd position, by the way, is 89. And you might want to convince yourself that 3489 is indeed a pair. Spoiler alert, it is. So maybe this is what we endeavour to prove now. Is it always the case that if you take two successive terms of the Fibonacci sequence in odd position, then you get a pair that satisfies this condition up here? If so, then the answer to this problem is yes, there are infinitely many such pairs. So how do we go about proving this? Well, because you're an Olympiad candidate, you are familiar with Cassini's identity. By the way, this is how far I got with the problem, because I'm not familiar with Cassini's identity. That's probably why I never competed in the Olympiad. Cassini's identity states that any Fibonacci term squared is one away from the product of the terms at either side. For example, if we choose 21, then 21 squared is 441, and that's one away from 13 times 24, which is 442. Now, we don't actually need this, but we need a similar result that holds for choosing numbers a distance of 2 away. This is actually a special case of something called Catalan's identity. And by the way, in the explanation that follows, I'm going to say odd term to mean a term in odd position. So these purple numbers are the odd terms, even if some of them have even parity. Now, I'll display the general form of Catalan's identity up here, but the case we need is that if we choose any odd term, then its square plus 1 is the same as the product of the previous odd term with the next odd term. For example, if we choose an odd term like 13, then 13 squared plus 1 is 170, and that is indeed the same as if we choose the previous odd term 5 and multiply it with the next odd term 34. But notice that we're pretty much done here. What Catalan's identity tells us is if we start with any odd term, say 13, then the previous odd term, like 5, will divide 13 squared plus 1, because we can multiply by something to get there. And it also tells us that the next odd term, like 34, will also divide 13 squared plus 1. Applying this identity as we move up the odd terms, we will always get that an odd term will divide the next one squared plus 1, and that next one will divide the previous one squared plus 1. I'll draw a little picture to really illustrate that. So here, imagine the Fibonacci sequence written out as odd term, even term, and so on. And underneath, we're going to write the squares of the odd terms plus 1. Now, Catalan's identity says, if you start from an odd term and take its square plus 1, then the previous odd term will divide that number squared plus 1, and so will the next odd term. Wherever I draw a red line, I mean divides. But that can be applied at every odd term. And this relationship continues forever. So if you take any two odd terms, they must definitely form a pair, because the first will divide the second one squared plus 1, and the second will divide the first squared plus 1. You can do this algebraically if you want to, but I find this a little bit more satisfying. So the answer to this problem is indeed yes, there are infinitely many such pairs with that relationship. So cool, and it's such a great property of the Fibonacci sequence that I had no idea about until I discovered this problem. Back to the film, Nathan is accepted onto the shortlist and goes to train in a maths camp in Taiwan. In a problems class, we're shown my favourite problem the film has to offer.
The vertices of a regular 72-gon are each coloured red, green or blue in equal amounts. Show that we can always choose 4 red, 4 green or 4 blue vertices such that each monochromatic set form a congruent quadrilateral.
Again, it's another very realistic Olympiad-style problem. We have a regular 72-gon with 24 red, 24 green and 24 blue vertices. They don't mention this in the film, but the colouring is random. We want to prove that there is essentially always a pattern of red vertices such that that same pattern is seen in the green vertices and the blue vertices. Again, pause if you want to work this out. It's a really, really good problem. There are likely many solutions, but here's a rather elegant one. Imagine picking up the red vertices and rotating them. Focus on the experience of this red vertex as it meets the blue vertices. In a full rotation, it'll meet 24 blue vertices. The same will be true for each of the 24 red vertices. That means the total number of matchings between red and blue vertices will be 576. We rotate through a total of 72 positions, so on average there are 8 matches per position. But the starting position can't have any matches, so to get an average of 8 per position, there must be at least one position with at least 9 matches. So let's pick one of those positions and put the red vertices down there. Now choose any of the 9 red vertices which are paired with a blue vertex. These are all vertices with a red and blue colouring. So pick up those 9 and we play the same game. Focus on the experience of this red-blue vertex. It will encounter 24 green vertices on a full rotation, so all of these 9 red-blue vertices will experience a total of 216 matches. There are 72 positions, so an average of 3 matchings per position, but again, the starting position has 0 matches, so there must be at least one position where there are 4 matches. Set the red-blue vertices down in that position and choose 4 which match with the green vertices. These are red, blue, green vertices all in the same position, which means they define congruent quadrilaterals. Since rotation doesn't alter the shape of each, we can set them down in their original position and we're done. It's absolutely gorgeous stuff. I love this one. Back to X plus Y, and the arc for Nathan throughout this second act is for him to gain the confidence to speak up during these training classes. The next time we hear a problem presented, Nathan actually solves it. So not only do we hear a fully presented problem, we get to hear a solution as well. First, the problem.
20 random cards are placed in a row, all face down. A move consists of turning a face down card face up and turning over the card immediately to the right. Show that no matter what the choice of cards to turn, this sequence of moves must terminate.
Here we're stretching believability because this is actually quite a straightforward problem, at least by the standards established by the film so far. I know because even I managed to solve this one. I think a more realistic Olympiad question would probably start with n random cards, and it would ask questions more along the lines of what are the minimum and maximum number of moves in order to get them all face up, or maybe turn it into a game between 2 players and discuss strategy. Anyway, my solution goes like this. Every move either kills 2 cards, or it shifts a face down card to the right. On repetition of moves, either all the cards die, or they all end up stacked on the right, at which point any valid move will kill 2 cards. And on repetition of that, all cards will eventually die. I could write that out a little bit more formally, but that's the idea. Now let's hear Nathan's solution. I can't actually show the full clip for copyright reasons, but here's how it goes. He starts by letting the number 1 equal down and 0 equal up, and then represents the string of 20 cards as a 20-bit binary number. Now, every move has the effect of reducing the magnitude of this binary number, and since this forms a strictly decreasing sequence, it must eventually terminate at 0, i.e. when all the cards are face up. So it's a similar idea to mine, but let's be honest, this one is much better. It's expressed a lot more clearly, and it's a little bit more elegant. Now, while writing this video, I discovered that YouTuber Mythologia has already made a video on this problem. So if you haven't seen that, it's great, you should go and check it out. The next problem we see is during the test given at the end of the training camp to select the 6 members of the Olympiad team. Each integer is coloured either red, yellow, or green. Show there always exists A, B, C, A plus B, A plus C, B plus C, A plus B plus C, which are always the same colour. I had no idea how to solve this one, and I can't find an elementary proof anywhere. The only solutions I've found appeal to some famous results, one of which is Hindman's theorem, which is a rather extraordinary result that says that if every natural number is coloured with exactly one of n colours, then there exists an infinite set of natural numbers d for which all elements of d and all finite sums of elements of d have the same colour. So obviously this is an extremely powerful result, and invoking it on 3 colours, we can extract D and choose 3 elements to prove the result here. There's probably a more elementary method that the question setters were expecting. If you can provide one, let me know down in the comments. This result though, man, That is pretty amazing. I might do a video on this one day because, I wouldn't understand it. Finally, we hear a problem from the Olympiad paper itself. There are 4 n² trains, and they are placed in a 2n by 2n grid, and each is painted one of 4 colours, and they are arranged in a specific way such that every 2 by 2 array contains a train of each colour. So no matter which 2 by 2 array we choose, we can find a train of each of the 4 colours. The colours are quite difficult to see on this blackboard, so I've given a number of dots or a line to each of the colours, so in case you're colourblind or just in case you can't see this at all, you can use those symbols to help you. Now the question is to prove that for all such colourings, the 4 corner squares of this whole grid will be 4 different colours. Again, I struggled to solve this one, but Mathologia poses this problem as a challenge at the end of his video, and I'm going to adapt my favourite response here. We'll start by asking, what is the total number of 2 by 2 arrays? So if we consider the total number of horizontal positions, the top left corner of this 2 by 2 array can be anywhere apart from the final column. So there are 2n subtract 1 horizontal positions. Similar reasoning demonstrates that there are 2n subtract 1 horizontal positions. So the total number of 2 by 2 arrays will be 2n subtract 1 all squared. And the crucial thing about that is that it's an odd number. Put a pin in that, we'll come back to it shortly. Okay, now we're going to add up how many times each colour will be counted when we count the number of colours across all of these 2 by 2 arrays. You'll see what I mean in a second. So consider just any 2 by 2 array. By the definition of this colouring, it must contain one of each colour. So every 2 by 2 array will contribute a count of 1 to the total of each colour. So for example, every 2 by 2 array contains 1 red, so therefore if we count the total number of reds across all of these 2 by 2 arrays, we'll have 2n subtract 1 squared reds. Now focus on the reds for a moment. Let C be the number of reds that appear in corner squares, E the number that appear on the edges, and M the number of reds that appear elsewhere. So for example, this is a corner red, this is an edge red, and these ones are middle reds. And we're breaking them down that way because if you consider how many times each one will get counted by these 2 by 2 arrays, a corner red will only be counted by the 2 by 2 array right up in this corner here. But an edge red will get counted twice. First by this 2 by 2 array, and then second by this 2 by 2 array. So because an edge square belongs to 2 different 2 by 2 arrays, it'll actually get counted twice when we do this count. For a middle red like this one, it'll actually be counted 4 times because it appears in 4 different 2 by 2 arrays. So therefore, what's the total count of reds? Well, it'll be 1C plus 2E plus 4M. But remember, we've already reasoned that there'll be 2n subtract 1 all squared reds when we do this count. So this is equal to 2n minus 1 all squared, which is an odd number. But how can this be odd? Because 4m is even, 2e is even, it must be the case that C is odd, i.e. C is 1 or 3. But there's nothing special about the colour red. Sorry to all the fans of red out there. We could apply the same reasoning to the other 4 colours. So C can't be 3, otherwise it would have to be 3 for the other colours, and there are only 4 colours. So C must equal 1 for each of the 4 colours, therefore there's 1 colour of each corner. No, there's not. There's 1 corner of each colour. It's another brilliant problem with a great solution. And that's actually it for the problems in the film. I'm honestly amazed that the film goes to such lengths to depict genuine problems and one real solution. And for the most part, the pitch and flavour of the problems are on point in terms of the style and level of Olympiad questions. So, excellent stuff so far. But how is the film itself? No discussion of X plus Y would be complete without an examination of its depiction of autism. Does this accurately depict the experience of autistic individuals, or is it a bit extreme and stereotypical? Well, I could talk for a long time about this, so I'll summarise here. All autistic people exist on a spectrum, but I prefer to think of it as a collection of spectra. Each symptom of autism can present mildly to extremely. In Nathan, we see presentations on the extreme end for a lot of them. This is relatively uncommon, but it does happen, so I can't really fault the film for that. What I love though is that the film never mocks autistic traits or presents them in a negative light. Let me just say as well that I am not a professional psychologist. These 6 categories are in no way official. It's just an informal way of classifying the signs and symptoms that I personally find helpful when discussing autism. We meet another autistic character, Luke, who is very blunt, direct, and brutally honest, traits which some autistic people display.
Yes, of course, though it may be the world's fastest developing nation, some of the cuisine doesn't seem to have advanced quite so quickly.
Oh, careful, careful.
This room seems reasonably symmetrical, apart from the window. Don't know about you, but I don't appreciate this forced proximity to each other.
What do you think, Nathan?
I don't know. Sorry.
People disagreeing with my opinion is one thing, but no opinion, we might as well not be here.
The level of his honesty is kind of funny, because he punctures the social norms that we're all used to, but the film isn't mocking him. If anything, his directness and the issues that can cause are depicted sympathetically. All in all, the film is respectful of the realistic challenges faced by autistic people, and by those who care for them. I would recommend this film for that reason alone. The only thing I take slight issue with is how Nathan's dad describes his son as having special powers.
It's like you've got these special powers, like a wizard.
This is well intentioned. Many of us enjoy and benefit from our autistic traits, but this stereotype that autistic spectrum disorder grants us superhuman abilities often ignores the very real challenges that some of us experience and appoints unfair expectations. Like I said, I could talk for a while about this, and I do in a companion video available to my patrons. There I break down the common symptoms and compare and contrast Nathan with my own experience of autism, which is very different to Nathan's. I also surveyed my patrons, many of whom are autistic, to explore the breadth of experiences. I do this because while I think X+Y has an accurate portrayal, I don't want anyone to come away from this video thinking that this is what all autistic people are like. If you'd like to see that, as well as extended cuts of some of my other videos, join our nerdy and welcoming Discord community, see behind the scenes updates, or if you just want to support my videos, please consider doing so on Patreon. So while I've praised X+Y for its mathematical accuracy and its depiction of autism, I actually don't think the film is great overall. Something that hasn't come up yet are Nathan's mum and his teacher. And by the way, this next section will include some very minor spoilers. Nathan's dad dies in the first few minutes, which serves to isolate Nathan's mum as the sole carer responsible for Nathan. Later, the absence of a partner for Nathan's mum opens the possibility of a romance between Nathan's mum and his teacher, Martin. Unfortunately, the film keeps cutting back to Martin, who suffers from multiple sclerosis. Now, I praise the film's depiction of autism, so I do give credit for its depiction of MS. It tackles the real issues that sufferers face, from the practical to the intimate. However, the film becomes very distracted by this B-plot that we're simply less invested in. You might be thinking that I'm only more invested in Nathan because he's autistic and that's where the maths is. But it's not that. The film is categorically about Nathan. Martin is introduced and developed much later, and the film offers no real resolution for Martin's character. Despite this, the film fills in a lot of screen time following him. To be as generous as possible, I think you could read this as setting up a parallel between the mental health issues faced by Nathan and the physical health issues faced by Martin. Martin even says that as his condition worsens, he might not even be able to hold hands or cuddle someone.
Because in a few years' time, we might not even be able to hold hands or have a little cuddle.
Nathan's difficulty with hand-holding is a frequent motif, and we do see that cuddling doesn't really come naturally to him. But it's shallow, and continually detracts from the engaging story that's already been established. Nowhere is this better exemplified than in my favourite scene of the film, which features Luke.
It's fine. I've done it before. Just got a bit carried away this time.
Up to this point, Luke is depicted as brutally honest and perhaps a little bit arrogant. Here we find him self-harming and struggling to cope with the expectations placed on him.
How did your mum and dad explain it to you? You found out. Mine said it made me unique. It's all right being weird, as long as you're gifted. If you're not gifted, then that just leaves weird.
Self-harming and depression, a common comorbidity with autism, are often overlooked in depictions of autism, and credit to the film for showing what can be the darker side of neurodivergence. Luke admits that he doesn't even enjoy mathematics, implying that he's only doing it to live up to the expectations demanded of him.
I don't even enjoy it. Maths isn't that stupid.
It's heartbreaking, and it calls back to that stereotype, the pressure that some people with autism feel when people expect them to have superpowers or an exceptional talent. This is what it can lead to. I'm really grateful for this scene and this character. I just wish the film tightened up its focus. This is where the story is, not with this B-plot. Something I really couldn't stand about the film was the score, which was by Martin Phipps, a composer I really admire. I love his score for the first ever episode of Black Mirror, which takes some of the most disturbing scenes ever aired on TV and makes them truly harrowing. If you've seen it, you know. But the music for X+Y, it's cheap, it's sentimental, it's obvious. How many times have we seen this kind of sad, clean guitar or sad piano music, just pasted over a scene to make sure we're feeling the right things? I'm sorry, it just doesn't do it for me. The film is also inspired by Daniel Lightwing, who did compete in the Olympiad. On researching the film afterwards, I discovered that his dad didn't actually die. Now, I'm 100% on board with changing real-life events in order to make a more compelling film, so this is fine, but another change they made is that Daniel's real-life mentor was actually a woman called Miggy Biller. Now, I condemn the film for this. Again, make changes if you want in service of the story, but there is a severe lack of representation of women in STEM, especially in mathematics, and there is nothing about this character that demands that he be male. You could argue the romance requires it, but I don't know, kill the mum and keep the dad. Make the relationship platonic, or make the mum bisexual, who cares? Some people won't be bothered by this, but trust me, representation matters. I've personally taught plenty of young women who have brilliant minds but are discouraged from pursuing mathematics altogether for fear of being singled out and othered in a predominantly male subject. It crushes me. I know I'm making a big deal out of this, but I just found it so unnecessary. I will say that Miggy Biller herself didn't seem to take issue with the change. She is quoted as saying that she chuckled at the line between fact and fiction when attending the premiere. Dan's dad, sitting just behind us, saw himself killed in a car accident. And I don't think I need to say that I didn't recognise myself in Rafe's ball. That was quite a bit of negativity, so let me end on a positive. I think Asa Butterfield gives a terrific performance. I've liked this actor for a while. I thought he was great in both the overrated Hugo and in the underrated Ender's Game remake. I'm a big fan of Rafe Spall too, and while I dislike the film's fixation with his character, his performance is really touching, as is that of Sally Hawkins, whose grounded portrayal of the challenges caregivers face lends additional emotional weight to the story. Before we rank the film on our 2-axis scale, I thought I'd share the most heartwarming take on the film that I've yet heard, and that is from Daniel Lightwing himself, who said, "I cried the first 3 times I watched it. It says things I was feeling, but could not express." X+Y has an impressive array of genuine mathematical problems and treats us to one elegant solution. It's not often we see writers do this level of homework and accurately depict not only the problems, but the culture among mathematicians. Couple that with its accurate depiction of autism, and I think I'm forced to place it very high on the accuracy scale. Overall, I have to say I didn't really like the film. It's mushy and sentimental, it's confused about where to focus the story, and the ending to X+Y didn't quite add up for me. Pun very much intended. Cube wasn't a great film either, but I have to say I thought its execution of the story it wanted to tell was superior. Yeesh. Feel like I might get some backlash about that one. But what do you guys think? Do you agree with my ranking? And what film should I break down next? Let me know, down in the comments. Thank you so much for watching. Sorry this one took a while, but I watched X+Y and was honestly surprised at how many great problems were on full display. And I thought each one was worth breaking down. They're great problems with fascinating solutions. The biggest thank you of all to my patrons who keep my channel alive, and if you'd like to see your name in these credits and get all the benefits I mentioned earlier, please consider supporting me as well. This has been another Proof Under Another Roof. I hope 2023 has been a great year for you, and I'll see you in 2024.